In this video, we're going to learn about enthalpy. Enthalpy helps us understand how energy is transferred during chemical reactions. When we study chemical reactions, we call the chemical reaction that's being studied the system. And this box right here is representing a chemical reaction that's going to take place as these atoms come together and form some new molecules. Everything that's outside of the system or outside this box would be the surroundings. The surroundings are basically the rest of the universe, and so heat can either transfer out of the system or it could transfer into the system. So in this video, we're going to learn what enthalpy is, and then we're going to look at an experiment that shows heat going into a system. We call that an endothermic reaction. And then finally, we're going to determine the enthalpy change during a chemical reaction. So we've already determined that energy is transferred between the system and the surrounding during a chemical reaction. And energy is either going to go out of the system or it's going to come into the system from the surroundings. Energy is expressed in two ways. It's either heat or it's work. Heat is simply changing the temperature of the system, while work is going to be making something move, and it's usually the surroundings moving away from the system. When discussing the energy change during a chemical reaction, we really only need to consider the heat part, and we don't really have to worry about the work. The short answer is work is dealing with changes in pressure and volume. And since the pressure change is going to be in such tiny little amounts during chemical reaction, we can assume it's just basically zero, that pressure is constant. And so that's going to bring us to enthalpy. Enthalpy is a measure of the amount of heat transferred into or out of a system. And you're probably wondering, why should I even care about enthalpy? Well, enthalpy can help us predict if a chemical reaction is going to supply heat to the surroundings or take heat away from the surroundings. It can help us best to determine what's going to help melt the ice on the road. And if you were to apply something like baking soda and citric acid and dump that onto the snow on the surface, it would actually just make it colder. While if you were to take some calcium chloride, also known as driveway heat, and dump that onto the snow, it's going to heat up and it's going to melt the snow really easily. And so our reaction of citric acid and baking soda, heat will go into the system, while calcium chloride and water is going to make heat go out of the system and providing that heat to transfer into the snow and melt the snow. So let's try that experiment of mixing citric acid and baking soda together. In this experiment, I'm going to add lemon juice. That's going to give me the citric acid into a cup. And then I'll add in some baking soda, just a spoonful here. But before I do that, I'm just going to take the temperature so I can see how the temperature changes. So the temperature is going to start at 20 degrees Celsius. That's just a little bit lower than room temperature. Next, we'll add in that baking soda. And this is going to be an acid-base reaction. The citric acid is an acid, and then the baking soda is a base. Now, as I add it in, it's going to produce some new compounds, and one of those compounds is carbon dioxide. That's where all that foam comes from. Now, we'll mix it up a little bit longer, and as I mix it, I can actually feel the temperature going down. It's a lot colder than the lemon juice started at as I picked up that bottle. And we'll stir it a little bit longer here, and then just take a reading on that thermometer. And a little bit hard to see, but the temperature has gone down to 15 degrees Celsius. So that's a difference of 5 degrees. It's 5 degrees lower than it was initially. So this is an example of an endothermic reaction. And the system, which is that reaction that was taking place inside the cup, was absorbing heat from the surroundings. And so when I touched the cup, I could feel that it was cold because the system was absorbing heat from my hand. Okay, let's get back to enthalpy. Enthalpy is a state function, and that means the calculation of enthalpy is pathway independent. In other words, it doesn't matter how you got to the end, it just matters where you started and where you ended up. And this fact makes the math really easy, since we're always going to be calculating the change in enthalpy of a system, that is, where the system started and where it ends up. Now, this change is in the chemical bonds of the molecules that are reacting. And so there's energy that's stored up inside of these bonds. And as the bonds break apart and form new bonds, the energy that's stored up in those bonds is going to change. And so that means if the energy before the reaction took place is higher than the ending energy, that means energy has to be released from the system. Now, it doesn't matter the order of the bonds that were breaking and how they were formed. All that matters is what were the initial bonds and what are the new bonds. It's kind of like if you were driving from point A to point B, and one method you could do is you could get on the highway and drive all the way down here and get off at point B, or you can drive all the way through these surface streets and end up at point B. Very, very different pathways. One's even longer than the other, but all that matters is that you started at A and you ended up at B. That's what a state function is. Okay, so let's try determining the enthalpy change for a chemical reaction. We're going to look at octane, which is a chemical compound in gasoline, and this is what your car engine is going to combust, which produce heat and then in turn powers your car. This reaction is exothermic because heat is going to be released. So here's a chemical equation that describes the combustion of octane. This right here is octane, and it reacts with O2. So these numbers, these coefficients, is representing the number of moles of each substance because this is a balanced chemical equation. So we start with 2 moles of octane, 25 moles of O2. That's going to produce 18 moles of water and 16 moles of carbon dioxide. It's also going to produce a bunch of energy because heat is released. And so I could write it as one of the products and say that this reaction right here is also going to produce, along with these compounds, 5,471 kilojoules of heat. But we normally don't write them right into the chemical reaction. So what we do instead is we show how the enthalpy changed of the system. So at the end of the chemical reaction, we put the symbol delta H. That means change in enthalpy. And then we're going to write down how it changed. So the enthalpy changed or decreased by 5,471 kilojoules. We say negative because we're always relating this change to the system, and we're looking at where it started, where it ended up. And so since the total enthalpy decreased and energy was given off, we put a negative sign right there. Whenever you see negative, we want to think exothermic reaction. And exothermic means heat is going to come out of the system into the surroundings. So let's try calculating the amount of heat produced for that chemical reaction. So this problem says, how much heat is released when 2 kilograms of octane is combusted in a car engine? First, we have to start with that balanced chemical equation. The beauty of balanced chemical equations is that they act like recipes. And so this recipe is for 2 moles of octane molecules. That's what this 2 is representing right there. All I have to do is figure out how many more moles 2 kilograms of octane is compared to just 2 moles of octane. And then I'll just multiply the amount of heat produced in this chemical reaction by that many times. So first thing we have to do is find the molar mass of octane. So I need to look at a periodic table and find out how much does carbon and hydrogen weigh. So here is carbon, has a molar mass of 12 grams per mole, and here is hydrogen with a molar mass of 1 gram per mole. Now there are 18 hydrogens and 8 carbons, so I need to multiply that 12 by 8 and then add it to 18. And so I can find that the molar mass of octane is 114 grams per mole. Now I can convert 2 kilograms into moles by dividing the mass by the molar mass. First I have to convert 2 kilograms into grams. To do that, I'm just going to multiply by 1,000. So I get 2,000 grams of octane, and then I'm going to divide that by the molar mass, and I end up with 17.5 moles. And so 2 kilograms is the same thing as 17.5 moles of octane. This recipe makes 2 moles, or needs 2 moles to make this much heat. So I'm going to find out how many times bigger is 17.5 moles compared to 2 moles. So I can take 17.5, divide it by 2, and I'm going to end up with 8.77. That's how many times bigger this number is compared to 2. Now I can multiply my answer by the heat from this recipe, and I end up with a total heat that's produced of 47,981 1 kilojoules. So did you learn everything in this video? Well, if you did, you learned that enthalpy is the heat going into or out of a system. You also learned that enthalpy is a state function, which means we're only concerned with the starting and ending enthalpy amounts. You also learned that endothermic means heat entering the system and exothermic means heat exiting the system. And finally, you learned that we can determine the enthalpy of a chemical reaction by using a balanced